Hello and welcome to Toddcast 18. I hope the sound is better this time. I realized there was a connection problem the last couple Toddcasts. So hopefully the sound quality is a little bit better, and most importantly, you're not getting the random external noises. But this Toddcast, we actually start what could probably be considered our first step into actual new material in terms of organic chemistry. We've done a few little things here and there, nomenclature, but this one in an organized fashion. Mechanisms are an observation or, I guess, a prediction of how the molecules transition from reactants to products. What bonds are formed, what is broken, the sequence in which it happens, how they have to be aligned to make these things happen. And so acid-base chemistry, our first reactions are now going to transition into other types of reactions and the pathway they go through. Okay, so with that in mind, I'll go ahead and start into mechanisms. So mechanisms, again, are a step-by-step, bond by bond, electron by electron transition from reactant to product. So proton transfer is one type of reaction. So that's the concept of a bronze-Lowry acid, bronze-Lowry base, where an acid is a proton donor, it transfers it over to a Bronson-Lowry base. So mentioned earlier, ammonia is a base, and it's a Bronson-Lowry base because it has a lone pair that can donate. It's a lone pair donor, which makes it a proton acceptor. So Bronson-Lowry is going to accept the proton. It's a Lewis base because it's going to donate a lone pair. It's doing the same thing. We draw arrows from where they start to where they end. So whatever pathway they choose, we're going to get there by showing the flow of electrons. Okay, so the lone pair donor, the Lewis base, attack the Lewis acid, or the Bronson-Lowry acid, the proton donor, or the electron pair acceptors, whichever way you want to look at it. Hydrogen cannot have two bonds. So when one comes in, one pair of electrons comes in, it is going to force the other electrons off. So that arrow, I need to draw this more carefully. So that arrow starts at that bond and goes to the chlorine. So I'm going to just let the computer generated one come in because I'm going to surrender. So arrows show electron flow from where they start to where they finish. So in the end, this arrow now becomes a bond from a lone pair to an atom. This bond becomes a lone pair. So very similar to resonance. So left arrow shows a lone pair moving to an atom to become a covalent bond. The right arrow shows a bond moving away, electrons moving away to become a lone pair on that chlorine. So in the end, you will end up with NH3 bonded to an H with a plus charge and a Cl minus. Okay. So in a chemical reaction, an acid-base proton transfer reaction again. Here's my base. So the lone pair, no negative charge, has a negative charge. I'm not going to be daunted by that. Just going to note a lone pair is coming in, and then recognize an acidic proton is HCl and recognize an acidic proton on the carboxylic acid. So it's going to be the exact same thing. Lone pair from where it starts, the right, this it's going to the right side of this atom is going to attack the left side here. Lone pair on the right is going to attack that. So the left arrow relative to the right one can attack there. That one's going to cause these electrons to be pushed away and go to O. So once again, the left arrow shows a lone pair moving in to become a covalent bond. The right one shows covalent bond breaking to become a lone pair on that oxygen. So in the end, the H is now here. This negative is now here. So you've just gone like concentration momentum. This hits here, which knocks this one out to the other side. Okay, for what it's worth, they need to line up in an almost linear fashion to make the orbitals overlap the right way for this to go. So I'm not going to be quite a stickler for the orbitals yet, but in time, that's going to be really important. So it should be a linear process, just like the hydrogen bond. Electrons come in to an orbital opposite of the other side. So to make it work out, it has to come in with correct orientation. Okay, substitution. This is our first OChem reaction. So as the name implies, you substitute. Just like in a sporting event, one person comes in and somebody goes out. So substitution, one group is going to go in, one atom is going to go in, one whatever it might be, nucleophile, and another one is going to come out. So it's not easy to predict right away, but if you had to make a decision, which element of everything here would come off and be happy as a negative charge? So when it leaves, it takes electrons with it. The chlorine is going to leave. So the chlorine, first step, the sigma electrons are going to become a lone pair. So if you do that, you now have this structure with a plus charge, and your Cl is happily off with 1, 2, 3, 4, 5, 6 electrons from the original, and then the lone pair it just got as a negative. It's gone, it's done, it is not going to come back because it is happy as a negative charge. What can come in though, so if you lost a bond, if a bond became a lone pair, then a lone pair has become a bond. So that can attack. And I'm drawing it on this side just because that's the one it's on, but it could have also attacked come around and attack from that side. It really makes no difference. Symmetry wise, both sides are roughly equal, but in the end, it won't matter because it's going to form the same compound either way. Okay, so sigma electrons become a lone pair. So the sigma bonding electrons become a lone pair. Lone pair now becomes a new sigma bond. But positive charges are not happy. So the electrons from here can come in that right there. But something has to take it off. Depending on the conditions, I'm going to draw the Cl coming in and taking it off. I don't know if there's a solvent in there. I don't know if another element will be better coming in. That's the only thing I have of the negative to come pull it off. It's you have to be given more information, like what conditions this is being done in. But for if these are the only two things you have, then it's either H plus going to be taken off by another sulfur or by the Cl minus. That's it. You have now officially become an O chemist. You've done a substitution reaction. So arrows start from where they're being lost to where they're being gained. So we always show arrows according to the way electrons flow. So this is a sigma bond, sigma bonding electrons, ending up in the chlorine, so a lone pair. This is a lone pair coming in and connecting to an atom, so we make a new bond. And then this is the H being pulled off, so that sigma becomes a lone pair. That lone pair becomes a sigma bond to the H, and you end up with HCl as your product as well. And again, all depends on the conditions of whether HCl will form or not. So if it's in water conditions, you would never get HCl. Fully dissociates. Gas phase or a oil, you might end up getting it, but it'd be really hard to get the Cl minus in the first place. Elimination, the second reaction, as the name implies, we're going to eliminate something. As a general rule, we usually eliminate water. So in bio, you may have learned something called the dehydration reaction. That's where you lose water from something. That's probably what we're going to do here. OH is going to be part of the water, but that's only an O and an H. We need one more H. So you eliminate two things. You eliminate an OH, one carbon, and an H from another. Okay, so I'm going to protonate it first. So lone pair on the OH becomes a sigma bond. So we now have an OH2 with a lone pair known as water. It is a great leaving group. So what it means is water is so stable by itself, it is going to leave. It's a group that will leave from this molecule. So those sigma bonds are going to come back and be a lone pair on oxygen. So sigma electrons are now bond, but we have a plus charge here. That's not very happy. You don't want a plus charge on carbon. So these electrons in this H can come and form a new bond. So the sigma electrons here, the electrons in the sigma bond, actually become a pi bond. So the new bond is a new pi bond. So that's just the end of elimination reaction. So the double bond should be drawn right here, if you can see it. So those two lines represent a double bond where it used to be a single bond. So arrow pushing, again, start with where the electrons are leaving to where they finish. Be very methodical early on. So again, just like learning a dance, use this analogy earlier, step through very slowly, go through the steps methodically, get it down before you go too fast. Go too fast, you'll make mistakes in your dance. Go too fast, you'll make errors on your homework and your exams. So get these down pat. The arrow pushing rules, they show the movement of electrons, not atoms. The nuclei doesn't move. So just like with resonance, we show arrow flowing, the arrows show electron flowing anytime I do it, whether it's in a reaction mechanism, whether it's in resonance, I'm always going to show it that way. So they start from this O and go to the H. So an OH minus reacting with HCl, these break here, so you end up with Cl minus like we did before, and water. Number two, double-headed arrows represent two electrons, single-headed represent single electrons. So if I show a double-headed arrow, that means both electrons are leaving. So I'm left with a plus charge on that central carbon. I'm going to draw it closer to the carbon. So it's not. So it's on that central carbon. And then I end up with a negative charge on that Cl. If I have single-headed arrows, so these arrows are starting from this bond here, and I'm going to just extend them a little bit. So this arrow is going here, and it's a single-headed arrow. This is going here, and it's a single-headed arrow. So let me get rid of my extra drawing. Artistic skills are not the best. So that means if one electron goes over, notice we have the 2, 4, 6 electron pairs, but now we have 1 from this bond and 2, 4, 6 from before, and lone pairs, but 1 electron. So these again are what's known as free radicals. This is known as homolytic cleavage. This is heterolytic cleavage. Hetero meaning unequal. Homo means equal. They're each getting 1 electron. And then arrows start at electrons. So let me get rid of the word free radicals because that just got in the way for me. So arrows start at electrons, lone pairs are bonds, not at charges. If you happen to be using the textbook for our course, the book gets this wrong actually fairly often. So just you do not start at charges. You always start where the electrons are. And they finish in an atom, then it's a lone pair. If they finish between atoms, then it's representing that they're going to a new bond. So this one starts at a bond, goes to an atom, pi bond, or sigma bond, excuse me, bond electrons become a lone pair. This one starts a lone pair, goes to an atom, so this becomes a new bond. So that bond right there is that pink one right here. And then that lone pair, let's say this one up here, represents that pair of bonding electrons. Okay, those are our rules. Not too much to them. They're fairly straightforward. So if you have this drawn in as such, that's going here. So the same thing we did up here, but this arrow showing the negative charge to the H. No, 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 no. Just want to emphasize, no, 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 no. You'll lose points for drawing it that way. Do not draw it as a charge to atom. It doesn't work that way. It's always from electrons to atoms. Okay, So there's not much else to add. We are now officially into the OChem portion of things. So thank you for a absolutely wonderful trek so far. Things in future podcasts are going to pick up pretty quickly. So I'm going to stop this one and I will see you at the next podcast. Bye.